course, in the chat you can write from where are you from and so on, as usual. And so we will comment about that later. So Alain, the floor is yours.
Okay, thank you, Alejandro, for the introduction. So I'm very glad today to attend to this second edition of the Artistic Project webinar series. So the title of my presentation today is about electrode manufacturing simulation using coarse-grained molecular dynamic and discrete element method. So as Alejandro told, I'm postdoc in the team. So today I will just present you the work that we did, the detail about the model that we developed in our team. So it's the idea of my presentation. So as you know, the aim of the project is to develop a computational platform that can simulate with that we can simulate the full chain of the manufacturing of the electrode. So starting from the slurry, drying, calendering, and so on. And as we know, the structure that we obtain after calendering will, for sure, the property that we obtain after calendering will depend. The property will depend for sure for the structure that we obtain after calendering. All the property that we have in that we obtain after electrochemical performance will depend strongly for the structure. So the idea generally is to try different chemistry, different composition, different particle size distribution in order to obtain, I would say, the best structure or the optimized electrode structure, because for sure the property will depend on the structure. We make all these experiments to have the best structure. Okay, so this is the I would say the main purpose of the artistic project is to investigate, to develop this platform that we can try different chemistry, different particle size distribution, different composition, and then make some kind of simulation to that to obtain different properties that allow us to play a role of predictor for in case of predictor for the experimental research. Okay, so as I told you, we have the workflow of the project starting from the slurry through the performance. But the thing that I want to point here is we start from the for the modeling, we start from the experimental information input as the chemistry, the formulation, and so on. And then with all these input, we inject that in our model. And then here we can see clearly two main parts, okay, the mesoscopic modeling and the continuum modeling. And today I will speak mainly about the mesoscopic modeling, so about the slurry, the drying, and the calendering. I will give you a few details about the model that we have in our team. So I'll outline my presentation. So I will, for the first part, I will speak about the coarse-grained molecular dynamic, and then the second point, I will explain you how we model the slurry and the drying process, and then the calendering part. I will take one example of the NMC electrode, and then just one slide about the electrochemical performance that we can perform after calendering. So for the slurry formulation, in the experimental point of view, we will mix in carbon or conductive additive, active material, binder, and solvent. And then with that, we also need a particle size distribution, for example, for the active material. Is like that information that we need at the beginning of the experimental. And then with mixing all this, we will obtain the slurry, okay? And then the idea is to see how we can model this slurry in our model. But as you know, we have different scale in when we mix, I would say, active material, carbon, and binder, or so on. Because, for example, if I take the size of the active material particle is around 150 micrometer, and the size of the carbon, for example, is around 50 and 100 nanometer. So you can see clearly that we have a very different scale in this problematic. So in order to make some simulation, the first thing that we know is, can we make the simulation of this kind of system, knowing that we have I would say, a very different scale, small size, for example, for active material, solvent and binder, or so on, and the bigger size for the active material. This is the first question that we need to answer. And the answer is, it depends, because for sure, if you want to simulate this, we have a huge amount of particles. For example, you will have something like 1 million of particles, and then you need for sure kind of super calculator in order to perform your simulation. And if you want also to study the different chemistry, and it will be very difficult, because we need to parameterize the force field that you use in your model and so on. So for sure, for the study that we want to do, we cannot simulate 1 million of particles in our system. Okay, so the idea is to find some kind of strategy to reduce the number of particles, and then that we can perform our simulation. Here you can see, for example, for active material, you can see clearly that you have primary particle inside active material particle, and for the nanoscale, you have a carbon, polymer, and solvent. So we want one strategy that we can make to reduce the number of particles in the model. So the idea is to use a coarse grain simulation. Just here to present you the idea of the coarse grain. For example, here you can see one image, SEM image of one electrode. One is the NMC 111 electrode, the 3D structure. Okay, yeah, in the micro scale level. And then if you make a zoom here, you can see clearly the big particle is the active material particle, and around here you can see some kind of small particle. So we can see this like a representation of this particle around the active material is a mixing of carbon and binder. So we can assume that we can see the model as the mixing of structure obtained by a mixing of active material and some kind of effective particle that combine carbon and binder inside. We call it carbon binder domain. And then if I take this small zone in green here, we have, I will say, in the mesoscale level. So to have this kind of, I will say, this kind of representation, this kind of simplification of the electrode in two entities, I would say active material and CBD, and then without consider any primary particle in the active material, and assume that we have a collection of the, I would say, carbon and binder, we consider this medium as a CBD particle. We are doing a coarse grain. Just this representation is just a coarse grain representation of our system. We coarse grain our system. Here I can show you some. You can see here, for example, an illustration of this coarse grain. Here you can see one molecule, and then with this molecule, we just represent. We just take an agglomerate of a group of atoms, as we consider a group of atoms as a single particle, as you can see here. And this coarse grain model is mainly used to simulate the complex system, as the molecule or the big molecule that we can see in the biology or the research team that is very complicated to simulate. So in this case, they will use a coarse grain representation or coarse grain simplification to allow to try to simulate the system, because if you want to simulate with the real size, it is not possible in terms of computational resource. Is very high. So molecules are represented not by individual atom, but as I say, by group of atoms. This is the way that we make the coarse grain. And by increasing by decreasing the degree of freedom, because if we make this coarse grain, we will decrease the degree of freedom. For example, the molecule will not have the chain of your molecule, for example, is not the real one. So you will decrease the degree of freedom of the mobility of the atom and so on. So you will not have the detail in the atomistic scale. You will lose this information, but depending of the property that we want to study, of the effect that you want to study, this can be neglect or not, depending on for what you want to do. And I think for our purpose is we can do this approximation, and it will be not have a big impact in our result. So how we coarse grain our model. So for example, here I present you the coarse grain model of the slurry. I will present you 3 strategies depending on the one we want to study. For example, the first one, we consider that we have a active material carbon binder, as you can see here, and an implicit solvent in our model. So we don't describe the solvent explicitly, but we describe the solvent as implicit medium. So we are particularly in medium, and the medium describe the solvent. So the interaction between the particle will change according to the fact that we have the medium is the solvent. This is the idea for the implicit strategy. So you can see clearly here the CBD. We have 2 particles, the CBD particle that contain carbon and binder, and the active material particle. And then you can see clearly we just consider a single particle for the active material. We don't take into account the primary particle. This is the first strategy. The second one is to consider active material as the previous one, but in this case, we have some kind of solvent inside the CBD particle. You can see here, the CBD particle is a mixing of carbon binder and solvent. Okay, so this one is the explicit solvent, but we take into account that in the CBD particle, we also have solvent inside. Okay, and then the third one is we consider that we have active material as the previous one. We have CBD particle, but without solvent inside. And then we have explicit solvent, like we have explicit particle in the model. Okay, so in this case, we have 3 types of particle. And then with that, we will reduce for sure the number of the particle in the system, because we coarse grain our model. For example, in the CBD particle, we have a collection of carbon and a collection of binder inside. So with that, we will reduce for sure the number of the particles in the system, and then we can perform our simulation. But in the rest of the presentation, I will focus on the second strategy. So the one with the CBD particle with solvent inside. Okay. So to obtain your slurry, as we say, we use experimental input. For example, here we study the NMC electrode. So we need a composition. For example, here 9433 binder, the solid content, and the particle size distribution, for example, for the active material. We use all these input, and then we use our coarse grain model to generate the initial structure of the simulation. So with all this information, we can calculate the number of particles of each component for active material and for CBD, and then we obtain the initial structure according to the composition and solid to liquid ratio. And then with the initial structure, we will now perform our simulation. But now I just want to, for the different step, I just want to show you the tool that we use. For example, for the slurry phase, to simulate our slurry, we use LAMS with the molecular dynamic. For drying is the same tool, And for calendering, we use light, but we can also use lamps. Okay, this is the tool that we use to perform simulation. Okay, for the slurry, we have input for experimental, we have the coarse pre-model, we generate our initial structure, and then we use molecular dynamic. For the principle of the molecular dynamic, the strategy is simple. You start with the initial structure, and then we give, I would say, initial velocity of each in each particle, and then with the force field that you use in your model, we calculate the force in each particle, and then we evaluate the acceleration, and then we integrate the Newton equation to obtain the velocity and the position, the new position of the particle. Okay, and then you iterate until you have the equilibrated structure, and then you can evaluate your property, for example, the porosity of your electrode, or you can evaluate the property that you want. Okay, at the end, and then you can compare this property with the experimental one, and then if it's not good, you will iterate, change the parameter, and so on. So you can see clearly here that to perform molecular dynamics, you need force field. You need interaction between the particles, because all these particles will interact. If you are in the slurry phase or in the solid phase, you have some kind of interaction between the particles. Okay, so we need to define to choose one force field, the force field that can mimic, I would say, the behavior of the interaction between the particles. Okay. So here I will present you the force field that we use. Okay. We use the granular Hessian force field. On why we choose this force field and not another one. The reason is, I would say, is very natural, because in our system we define we make some kind of coarse grain. So we have some kind of particle. We not have I would say atom, as we not in the scale of atomistic scale. Okay, we are in the mesoscopic scale, and then we have grain. Okay, we have some kind of grain. Okay, and the force field that we can use to, I would say, simulate the interaction between the grain is the granular force field, and we have, I would say, 4 or 5 type of granular force field, but depending of the system that you study, you can choose one to another. But in this case, we use the Asian one, and I just want to explain you a little bit how this force field work. So you have, for example, if you have 2 particles, okay, the particle interact like you have some spring between the particle, okay, and then for example, the Kn and the Kn parameter is like a stiffness of the string, okay, and then you have also the damping part. You can describe some kind of damping between the interaction of the particle. This one is the gamma n in the normal interaction, because you have the normal interaction and the tangential interaction, and you have this part is for the normal interaction, and the second one is for the tangential interaction. Okay, so we have 4 parameters here, okay, for the granular force field, and then you have active material and carbon binder. I would say we need to define the interaction between active material, carbon binder, and between the carbon binder. Okay, but this force field is mainly repulsive. Okay, and then if we want to have some kind of attraction between particles, is some kind of attraction, because we know that if we have binder and carbon, we have some kind of agglomeration in the CBD particle. So we need some kind of attraction between the particles. And then for that, we choose to use the simple Ngandjong force field to simulate some kind of attraction between the particle. Okay, so here we have two parameters. So in totally we have 6 parameters, and for sure the electrode property will depend of these 6 parameters. So we will now make some kind of parametrization to reproduce the experimental result, I will say, by playing this force field. So for that, we need to validate the slurry part and the electrode, the dry electrode part. Say for the slurry, we validate viscosity and density, for example. And for the electrode part, we have porosity, density, pulsar distribution, and also mechanical property for the non-calendar and the calendar electrode, for example. Okay, for the slurry phase, we start with the initial structure. We use molecular dynamics with the force field, and then we simulate with to obtain a slurry. We perform the NPT simulation, means that we have a number of particles fixed, temperature fixed, and pressure fixed. We optimize structure in order to have a equilibrated slurry. And then we have to play to these 6 parameters. Okay, this is the idea. And then at the end, we obtain our slurry. After obtaining a slurry, we need to validate the slurry. So we perform the non-equilibrium molecular dynamic. Okay, as you can see, we apply some kind of shear rate. So we apply a deformation of our box, and then with that we evaluate the shear stress, is the force divided by the surface of the plane, and then with the shear rate and shear stress we can evaluate the viscosity of our slurry. And then we play with the parameter in order to reproduce the experimental result. As you can see here, for the density and viscosity, you have a good fitting of the viscosity at different shear rate, and also for different solid to liquid solid content. You can see clearly the point is the simulation and the line is the experimental result. And for the density also, we have good agreement. So now we can go to the drying process. Here in the simulation, we do not simulate the coating yet, but we can propose something about the drying process. So for a drying process, I will say we have different approach also to simulate the drying. The first one is just to shrink the CBD to remove the solvent inside the CBD by just shrinking the CBD, and then we relax the system. We change the interaction between the particle because the interaction change, and then we simulate, we equilibrate the system. And then for the second strategy, we can shrink the particle gradually, step by step, and then after that we equilibrate also the final structure, with the final size of the CBD with that solvent we equilibrate. And then the third strategy that Theo Lombardo for sure will present tomorrow. Okay, a nice presentation tomorrow for Theo Lombardo is
Alain, you have 5 minutes to go.
Yes, is to, for example, have different evaporation rate, for example, take into account that we have evaporation rate, and then you can have some kind of evaporation along the thickness, heterogeneous evaporation along the thickness. Okay, so we validate also the drying electrode by, for example, have the fitting the porosity and the density. As you can see here, the experimental result and the simulation one. So you have a good agreement with that. And then another thing is to, for example, validate the mechanical property. Okay. For do that, we use a DIEM simulation. Okay. So for a DIEM simulation is like I will say for the method that you use for the DIEM is almost the same as what we use now. It's just that we take into account that we have the rotation of the particle, the property of the material. The particle that we have is linked to the real property of the real material. So you have some kind of mechanical property that you have to put in the particle. Okay, but the strategy is almost the same. So you apply pressure in your electrode in order to reduce the porosity, okay, and to increase the contact between the particles. This is the idea, and we do it with the DIEM simulation. Just to show an experimental observation that we have when you apply the pressure, you will reduce the porosity, as you can see here in the paper published by Emiliano. For different composition and different solid to liquid ratio, you have different porosity, different response, okay, of your electrode. So it's not a simple thing to simulate. Your model need to capture all these difference. And for pore size distribution also, you can see here that the shape of the pore size will be different depending on the composition that you use. So just to say something about the DEM, as I told you, it's just a way to capture the granular medium with, you can simulate the solid or the liquid behavior of your system, okay? And then the idea is almost like a molecular dynamic. So you start with the initial structure and then you calculate the contact, the force, and so on, okay? And you iterate. Here just to show you how depending on the overlapping between the particle, the interaction between the particle will change. You have a repulsive and attractive, because here we have some attractive interaction that we add in our system, okay? Depending on the contact surface between the particle. And then we perform calendering. Now to validate our mechanical property, we need to validate, I will say, the indentation curve. For example, here you apply indentator, and then you remove, and then you evaluate I will say, the plastic and the elastic part, okay? And then with that, you can evaluate the hardness and the Young model also. So the idea is to validate our mechanical property with the same strategy. So we perform indentation in the simulation, and then we validate our mechanical property, and then you can see clearly that we have a good agreement for indentation and the porosity versus pressure. We have a good interaction, good fitting. Okay. And then we can also evaluate, characterize the structure. For example, here we evaluate the tortuosity and the pore size distribution. You can see here we don't have the exact value for the pore size distribution, but the shape is almost the same. When you calendering, you reduce the big size and then we increase the small size and so on. And then you can see clearly for the tortuosity that depending on the direction, you will have you have some kind of plateau, and then you have the change of the tortuosity in each direction. So to conclude, I just want to say that the structure that we obtain after calendering or after drying, you will inject it in the continuum simulation, for example, in order to obtain for example, the discharge curve, the capacity of your electron, and so on. And in the team, Mehdi Soushan developed a nice tool called Enough to mesh the 3D structure that we obtain. And then he will present you, I think, tomorrow, this tool. And then we use COMSOL to perform our simulation. And here you can just see one simulation, for example, that we perform to take into account the effect of calendering in the electrochemical performance. You can see when we apply calendering, we decrease the porosity, and then the specific capacity for the calendar electrode increase, for example, here. And to conclude, here I present you a strategy to implement the simulation of the slurry and the dry electrode with using CGMD simulation. And also we investigate the calendering process by using DM simulation with strong link with experimental result. And for sure, for the perspective of our work, we want to apply the same strategy with for different chemistry, and take into account, for example, the effect that we have a primary particle inside the active material for the calendering step. And thank you for your attention.
Thank you very much, Alain, for the great talk. So, Professor Alain, very nice. I think I think people like your talk a lot, and there are several questions awaiting for you. So maybe Fernando, you can start.
Absolutely, yeah. We have many questions for your talk. So, Alain, here, Asanfi G. Nasena asks, how does the amount of solvent in the slurry affect these results? Simulations or experiments? ? Especially on the slurry viscosity, evaporation rate, etc. So, a very broad question, I think.
Okay, thank you for the question. Yes, in our model, I would say in the model and in the experimental part, for sure the amount of solvent will play an impact in the for example the viscosity part, as you can see here. When we make a fitting of the viscosity, for example, here we perform simulation for different solid to solid content. So the amount of solvent change. You can see clearly, for example, you have 69, 17, 71, and so on. So we increase the amount of solid content, so we decrease the amount of solvent. So we can see clearly that the fact that we change the amount of solvent in the model or in the experiment, you will change, for example, the property of the system. For example, the viscosity of your solvent will change. So I think in the model we can change according to the composition. You will have a different number of different, I would say, volume of the solvent, the volume of the solvent in the CBD, if I can explain that, because in this model the solvent is inside the CBD. So if we change the solid content, we change, I would say, the size of the CBD. It can increase or decrease depending on the amount of solvent you have, in order to match the solid to liquid content. So and if we change that, for sure we will change the property, for example, of the slurry, and then I think it will have an impact in the, when you perform the evaporation, it will have an impact in the final structure upon drying process.
Fantastic. Thank you for your answer, Alain. Here also we have Hicham Machiruki, who asks, number one, how you set up the values of your 6 parameters for your LH, so your Lennard-Jones and your GH forces, and 2, how you relate the drying process to the temperature and the direction of the heat source.
Okay, good question. Okay, for the parameter that we use, okay, as you know, and when you perform the simulation, we don't, I would say, you have an idea of the range. I will say that, for example, for the I will say the stiffness of the particle, because if you know, for example, the Young modulus of your particle, you can guess, I will say, the order of magnitude of your of this kind parameter, for example. For the damping factor, we don't know exactly, because we don't have any experiment that gives this value. So you will start with, I will say, one value, okay, and then the thing that we will do is to gradually change the parameter by manually, or use some kind of automatized tool to change the value that will give you, I will say, nice fitting of your viscosity, or of your I will say porosity, and so on. So we make some kind of optimization of the parameter in order to reproduce the experimental result.
Excellent, thank you.
Yeah, we use also Alain, maybe to add just a comment on Alain. So we also use particle swarm optimization and machine learning to fit the parameter, to accelerate the fitting of viscosity curves in particular.
Okay, so here we have another question from Guillermo Bomchil. She asks, do you consider somewhere the difference between the use of lithium hydroxide and lithium carbonates, e.g. calcination temperature, to obtain the NMC active material from the precursor?
In our study, no. In our study, no. Yeah, now, no. But the idea of the model is to use, we can use, I would say, different chemistry, but for sure, depending on the chemistry you will use, okay, for sure you will change, I would say, the observable. For example, if you use one material or another material, you don't have for sure the same result. So according to the material that you will use, we will make some kind of parameterization. The result will depend on the material that you have. So.
Perfect.
Yes.
Okay, I'm going to move forward because we have many questions. Sorry, Alejandro,
Yes,
you wanted to say something?
Yes, Fernando, if you can take a look in the moderator chat, please. So we need your assistance.
Okay.
So I will continue with the questions. Don't worry. Okay. Okay. So next question is from Anshuman Chawan. So thank you for a nice presentation, Alain. So how do you determine the size of the CBD coarse grain? Is the size distribution of CBD particles also considered? If not, what is the maximum CBD coarse grain size considered?
Okay, nice question. For the size of the CBD, I will say we evaluate the number of CBD particles by taking into account the density of the solid CBD and the composition, because with that we can evaluate the volume of CBD, the solid CBD, I will say that. And then with this number of CBD, you will add the amount of solvent that you need to have the good solid to, I will say, the solid to liquid ratio. Okay, so you start with the size of the CBD and you increase this size to obtain, I will say, the volume of the solvent that you need in your system. This is the strategy that we use. And then for the maximum size, I will say it depends. For example, for our study, now I will say we are in the range of 2 micrometer to 6 micrometer, for example. But I think that this range, you can play with that. It's not a fixed value. You can also study the effect of this, for example, this size if you want. But in this case, we don't want to study the effect of this size, but to just evaluate the volume that we have to increase in the solid CBD to obtain the same solid to liquid ratio. And then for the fitting, we play with the force fit, not the size of the CBD.
Great. Thank you, Alain. So, yes, there was a question from Alexis Dafour. Thanks, Alain. Very nice talk. What will be the computational impact of considering solving both inside and outside the CBD particle? It will be much more accurate, wouldn't it?
Yes, good question. We don't know, but I can say that for sure, maybe it could be accurate, but we can see clearly that here we use the strategy, but using the CBD inside the active the CBD. Okay, but we have another strategy. I think maybe Theo will present this result tomorrow. Okay, the fact that we use CBD the solvent outside the CBD, but in any case, you can see that you will need to make some kind of parameterization, because you will not have the same, I will say, parameter that you obtain for this model with the model that you have with the solvent outside the CBD. Okay, maybe it will be, I will say, can mimic the real, I will say, is more close to the real slurry, but we need to parameterize your system. If you use this one, or you use another strategy, or you use some kind of implicit solvent. For example, with the implicit solvent, I think the simulation will be much faster. Maybe you can explore many things, but for sure you need also to make some kind of parameterization. So for me, I don't think that you will have you have some kind of ideal model for that, I think.
Okay, great, Alain. Thank you.